Log on, tune in, find out. Another good idea from Cambridge.
The first talk will be by Adrian Nachman from University of Toronto, Reconstructing Conductivity from Minimal Eternal Data. And you know Adrian Nachman as one of the founders of the multidimensional bus problem. Of course, everybody knows his two-dimensional paper and his construction for solving inverse boundary problem. But now Adrian will be speaking about reconstruction conductivity from minimal internal data.
Thank you very much, Slava. It's a pleasure to be here. So I want this to serve as somehow an introduction to this new sub-area of inverse problems where the data is on the inside. You've heard already Gunther's beautiful lectures last week on such problems. So here I'll give you some quick examples of problems where somehow by combining two physical approaches, which is why these are sometimes called hybrid methods, we try to get more information than is traditionally available from inverse boundary value or inverse scattering problems. And one of the most successful inverse problems is elastography. There we have elastic waves, the oldest method of diagnostic, which is palpation. We send an elastic wave inside the body, and we watch it with another method. We watch it with MRI or we watch it with ultrasound. And this is then combined in an inverse problem to deduce the elastic properties of tissue, the stiffness and so forth. It's successful in that it has been built in to MRI machines, for instance, and there are now already thousands of people who have been sent to have an elastogram, for instance, to check for liver cirrhosis, as opposed to having a biopsy. I'm going to talk about topic 2, where we're going to combine what you've heard here as the Calderon problem. You've heard me talk about it last week. Lovely problem, beautiful mathematical structure, as I tried to convince you. Trouble is it's extremely ill-posed. Not our fault, but there it is. So suppose that you are still convinced that finding the electric properties of tissues is a useful thing to do for diagnostic purposes. We function electrochemically, and so could we somehow, what can we do if we want to find the electric properties of tissue? And I'm going to show you how we can combine it with some MRI information to try to overcome the limitations of the severe ill-posedness of the inverse boundary value problem. And you heard Gunther talk about photoacoustic tomography, where we combine light and sound. Light is like lightning that produces a sound wave, which we then collect with ultrasound transducers. And again, that somehow manages to capture advantages from both modalities. So here's the plan of the talk. First, I'm going to tell you about something which is very old and which I had nothing to do with, which is this method of current density imaging, which is at the source of a lot of methods that combine EIT and MRI. And my main purpose for talking about this is to convince you that we can, in fact, get good inside information, interior data. So the story is that Mike Joy's group at University of Toronto invented this in the early 90s. When I came to Toronto around 2001, and I heard about how they can find current density imaging, my contribution was to add an I, going from current density imaging to current density impedance imaging. If you know currents, can we find the conductivity? And most of the talk will be about this, because this, I think, is mathematically much more, much less trivial and more interesting. Even, I apologize to those of you who've seen most of this talk before. Alexander Bougain wanted to make sure you remember everything he said in Banff. I go the opposite extreme. I hope you've forgotten everything you've heard me say, so that you can enjoy this like a fresh product that it is. And there is something nobody's seen before, or I think nobody in this room, which may come at the very end. This is now recent joint work with Amir Moradifa. I'm a postdoc at the U of T, where we've taken this problem and we're now allowing perfectly conducting and or insulating inclusions. All right, how do we get interior data? So you have to understand a little bit about MRI. It usually takes me about half a semester to explain MRI. So now I'm going to do it in about 3 minutes. Therefore, it will not be a serious explanation, but just to give you a feel of it. So an MRI machine has a huge magnet, which has a static magnetic field, usually called B0. And the purpose of that is to align somehow, usually you're told all, but in fact, not at all protons in the body to start spinning more or less in a consistent direction. Otherwise, their contributions cancel out. And the thing to remember is that they spin with a frequency called Larmor frequency, which is proportional to the size of this magnet. Now, one then gives them a little push at this frequency called the resonant frequency from another radio frequency coil. And once you stop that, they tend to relax back. And as they do, they send a little signal, which we collect. And that signal, after a lot of simplifications, is basically the Fourier transform of this magnetization. And as a Fourier transform, it's a complex number. What doctors tend to look at is the magnitude of that complex number. We're going to get our information from the phase of that complex number. How do we do that? Well, suppose you apply a current. A current will create a magnetic field. If you would do this inside the MRI machine, you can imagine this extra magnetic field being added to B0. And so it will, if you remember what I just said, it will speed up the rotation frequency of these protons. Speeding them up, since we are expressing things in complex numbers, means adding something to theta. And that's why by subtracting the picture we get with the current applied and the one without, in the phase image, we will learn about the size of the applied magnetic field corresponding to our current. And once you have the magnetic field, you have Ampere's law, which gives you back the current. Now, this is easier said than done, because what happens is only the component Bz along the huge magnetic field makes a difference in what you see in the speed up. And if you only know this part of a magnetic field, it's kind of hard to compute the curl. And now there are different approaches to this issue. What the Mike Joy group does is they rotate the subject. So in particular, it cannot be done on people. to obtain the other two components of B. There's a big group in Korea which started out also from the Mike Joy invention, but went into a different direction. They call it the BZ algorithm, where they only take this information and they couple it with the PDE to somehow recover the conductivity. And that has the advantage that you don't have to rotate, but then you pay the price in that things are non-local. If you have regions like the lungs when there's no signal, you have to worry about these elliptic PDEs and so forth. So this is just a picture to show you that this is actually being done. So one of the people, the company supporting Mike Joy, is a defibrillator company. So defibrillator is these big voltages that you apply when someone's heart needs a boost. And the sort of questions they may want to ask is, where should we place these electrodes when I give you this shock? Is it because we'd like to have the most effect with the least voltage? So is it better if I do it like this or like this or like this? We're one of the few groups in the world which can tell them where the currents go. So here you see these little arrows with computed current densities from the data obtained in the MRI machine. And you only see a few curves here just because otherwise the picture would not would be incomprehensible. So this is really a piece of software where you pick one of these dots and then it will fill in the integral curves for the vector field. And so here you see some. And by the way, it tells you that the heart is indeed very anisotropic. And for the rest of my talk, I will nonetheless assume the conductivity is isotropic. We don't have any results for anisotropic conductivity. So this problem has been looked at by a number of people, even some Bill Lionheart, who's in the room, as a huge system of hyperbolic first-order ODEs. And something we found is that, in fact, if you have two currents, so here's one current, here's another current, there's actually a formula for the gradient of log sigma that is explicit once you have those two currents. This has independently been discovered by Lee. And the group in Toronto really loves this, and they started making experiments. And I'm going to show you this experiment, which is aimed mostly at the people who have seen pictures of EIT results. Because the idea is we're trying to say that with this kind of data, you can do a lot better than with EIT. So in particular, resolution in EIT decays exponentially in the distance from the boundary. That's something that's already understood analytically. So in this experiment, you will see as I place the electrodes, so we'll do two currents, and the electrodes are placed here at the top of this phantom. And that's done on purpose. So normally you'd think you put them one on top and one at the bottom to get as much current through as possible. We wanted to see how bad things go as you move away from the electrodes, from where you make the measurements. And here you see two computed currents from this data. And again, I asked them to make this phantom star shape because this is the sort of thing that EIT does not image well. And so here are the results. So the main person who did the work on this is Wei-Jing Ma, one of our PhD students who's now a postdoc. And one thing she did is she color-coded these slices through this 3D object. So this is a 3D reconstruction. So I think this one is on top. And as you go through these, this is the furthest one from the electrodes, and you can see that the resolution stays pretty good as you move away from the boundary. So this is supposed to convince you that we're in a different situation than in EIT. Okay, so that finishes topics 1 and 2. I'm now going to talk about the problem where instead of 2 currents, we only use 1. That's important because it cuts down acquisition time. For each current, you have to essentially make a separate experiment. But honestly, for me, it's important because the mathematics turns out to be really nice. And in particular, I'd like to explain to you, this is a workshop that talks about geometry and analysis connected to inverse problems. I'd like to show you how in this problem, even though it's an elliptic problem, we bring in some nice geometry. Another reason before I forget is, so this is just a question that Alex Tamasan and Alex Timonov, who were working with me at the time, they were saying, what if we have less data? What if we just have this? There was no solid motivation why they were asking this. They just tried it one day at the pub. So right now we're doing something stupid. We are making the experiments, rotating 3 times or twice to find the full J, and then taking the magnitude of J. But the issue is maybe there is a physical experiment. Maybe it doesn't even use MRI. Maybe some temperature measure, something that somehow will get us the magnitude of J. And with that, I'm going to show you what we can recover. All right, so let me remind you of the conductivity equation. You've seen it this morning in Mati Lassas's talk and lots of times last week. So sigma is the conductivity which is unknown. And what do I mean by current density? By Ohm's law, voltage drop divided by R is the current. So that is the current. Suppose we are, so in the forward problem, you know sigma and you know F. You calculate the electric potential. In this particular inverse problem, we know F. We don't measure it. It's sort of imposed by us. This is our what we decide in the experiment. And as opposed to Calderon's problem, where you do lots and lots of Fs, in theory infinitely many Fs, and make the corresponding current measurement on the boundary, here we just do it once. We apply one F on the boundary, we measure the corresponding J, and we don't measure all of J, we just measure the magnitude. So this is what I mean by minimal data. And minimal is in some sense a pun because of what I'm about to show you. Okay, so let's take the magnitude. So this is a basic idea which I think first Seo thought about it. Okay, if you know magnitude J, calculate sigma as, or substitute sigma as this quotient, put it back in the equation, and you get this nonlinear degenerate elliptic PDE. And degenerate elliptic, take it with a grain of salt. It's not really an elliptic PDE. So just to stay with Seor, they looked at a corresponding Neumann problem and were quickly discouraged because A, the Neumann problem sometimes had no solutions, and B, when it had solutions, it had infinitely many. And so we were lucky, we looked at the Dirichlet problem instead. So you might say, end of story. This is my data, magnitude J. If I know, I solve this Dirichlet problem for this nonlinear PDE. Once I find U, I can immediately find the conductivity. The problem is that this Dirichlet problem has infinitely many solutions. So that's not a good way to solve the problem. But before I do that, sorry, let me tell you a few more things. In Mikko's talk, following right after this one, you will hear about the P Laplacian. When magnitude J is 1, this is corresponds to what he will write down. In his case, P will be bigger than 1. Here, P equals 1. So this is a variable coefficient one Laplacian. And basically, our starting point was the observation that this equation says that the mean curvature of the equipotential surfaces has to be 0. So it's not a deep result, but it's something that was not observed before, and it's news for physicists. So we can say the following. Take this electrostatic situation, and it's stated here as our first result. The equipotential surfaces, which are the level sets of U, are surfaces of 0 mean curvature in a metric given by magnitude J. So this is a new fact even for harmonic functions. Take magnitude J is 1. If you, take sigma is 1, you have a harmonic function. Let J equal magnitude grad U. Hold on to that. Then equipotential surfaces are minimal surfaces in a conformal metric given by magnitude J. So that was our starting point. And so the first disappointment is this example, which comes from Sturberg and Ziemer. They looked at the problem with magnitude J is 1, which is a problem that was studied quite a bit in the theory of minimal surfaces. I will come back to this in a moment. And so what they showed, now this is as I said, a degenerate equation. You have to be careful how you interpret this. But now the metric is Euclidean, and the easiest way, so they usually describe solutions in viscosity sense. You don't need to know about that. The way to think about this is the level sets of U, we're in 2D, have to be straight lines. That's what it means for you to solve this equation. And so they have the following family of examples. You take any lambda between 0 and 1, minus 1 and 1, maybe even and you take for boundary data, you take x1 squared minus x2 squared. So that's f. So f is basically cos of 2 theta on the boundary. And so cos of 2 theta equals lambda in 4 places. Let's say here, 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 and here. So you make a rectangle with those 4 points on the boundary as vertices. And you declare that u is identically lambda in here. And the rest you fill in with straight lines like so. So these are the level sets of u. And that's written out for you over there. So it turns out for every lambda, this is a solution of this Dirichlet problem. So there are infinitely many solutions. Now, what saved us is a nice hint we got from the work of Sternberg and Zimmer. They were actually studying the so-called least gradient problem. So let's look at the minimum of this, where u is equal to f on the boundary. So this is the variational problem for which this is the Euler-Lagrange equation formally. And the reason this is interesting goes back to a famous paper by Bombieri, De Giorgi, and Giusti, who precisely pointed out that the level sets of such a function are not just minimal surfaces, they are area minimizers, and use that to prove that a certain cone in 8-dimensional space was globally area minimizing. And this was important in the theory of minimal surfaces. So up to dimension 7, there is no such cone, and that implies that solutions of minimal surfaces are regular, but in 8 dimensions, there is in fact a counterexample, and this is how they prove that it's area minimizing. So this was a problem that was had its own history, and what Sternberg and Zimmer point out is that of all these u lambdas, only u sub 0 minimizes this. So this is a hint that if instead of the PDE you look at the variational problem, there's a chance to have uniqueness. Okay, well, do we have a right to look at the variational problem? Let me show you that indeed we do. So let's go back to our problem. And let's suppose that J comes from this. So let me put knots up here, or maybe just leave it as U, and let's call this a V. So assume J is indeed what we call admissible. So this is just some positive function A of x, in principle any function. Now I'm going to say it's not just any function, it comes as the magnitude of a current. Okay? And so let's look at the variational problem in V. Can you see, Slava? Okay. So here I'm going to use Cauchy-Schwarz. This is bigger than sigma grad U dot grad V. Now I'm going to integrate by parts. If I put the divergence operator on sigma grad U, I'm going to get 0. And so this will leave me only with a boundary term V sigma du d nu. So if V is any competitor of U, which equals F on the boundary, you see that magnitude J times grad V is going to be bigger than or equal to this number, which only depends on F and this. So amusingly, this is the Dirichlet to Neumann map applied to F. So, and of course, if V equals U, then you have equality here. And so this tells you that this is the minimum. And it tells you that U, the function we are after, is a minimizer. We don't know if it's unique, but at least we know it is a minimizer of the problem, this, with U equal F on the boundary. Right? Any other one gives you a bigger number. So this shows us that it's okay to forget about the PDE, the degenerate PDE, and look instead at the variational problem. Okay. All right, here I made a note to myself not to forget, I almost did. There are a number of other hybrid methods with very different physics done by some of these distinguished people. So for instance, the first one combines EIT with ultrasound. And the idea very briefly is you make EIT measurements. Now you take ultrasound and focus at a point. This is assuming you can do that. And you make EIT measurements again. And by comparing those two, the EIT without the ultrasound and the EIT with the ultrasound focused at a point, and you make a little asymptotic calculation, you get sigma grad U squared instead of our sigma grad U at that point. And then you focus at a different point. And so by sampling, they can find this quantity inside. If you substitute that in the PDE, you get something like, so sigma is, if this is, I don't know, let's call it B. B over grad U squared, grad U. You get to something we might call the zero Laplacian. And there are these various other Gebauer and Scherzer, Ball and Schottland, different physics, they all end up with the zero Laplacian. And so this is to tell you that this is just part of a little new area in inverse problems. It's also to tell you that we were lucky to have, well, A, done it first, and B, gotten the one Laplacian that has this beautiful geometry attached. Okay, this is the proof I just gave you. That the function you are after is indeed a minimizer of that functional. This is a deeper result inspired by the Bombieri, De Giorgi, and Giusti paper, where we show that not only is this trivially a minimal surface, in other words, a critical point of the functional, but level sets are in fact area minimizing. And you have to be a little careful on how you state this because of geometric measure theory technicalities. Okay, so as I hinted at before, we're going to now look at data which is admissible in the sense that it comes from a conductivity. And our results are for such data. And if you think about this example, by this definition, this would not be admissible. So the claim is that A equal 1 cannot be the conductivity, cannot be the magnitude of a current for this U equals this F on the boundary. So essentially, by uniqueness, you show that this is the U. If there is a U, this has to be the 1. And this U is constant here, so the gradient is 0. If the gradient is 0 and this is 1, then you don't have a sigma. This is what I used to say. So just a preview of what's new. When we started looking with Amir at situations with perfect conductors and perfect or insulators, we have now extended the results and extended the notion of admissibility to a situation where this would now be a perfect conductor. Right? You want to say sigma is infinity. So we can now consider this admissible if you allow me perfect conductors. But that's coming later. For now, the data is admissible if it comes from a conductivity. And there's a little characterization of what I mean by admissible data. This I already showed you. If it is admissible, then the corresponding electric potential is a minimizer. And since magnitude J over this is sigma, it will be a bounded function which is positive. Conversely, if I give you F equal A grad U, and you have a minimizer, this is sort of semi-trivial, but you get hold of a minimizer with the property that this over this happens to be in L infinity plus, well then hold on to it, that's your conductivity, and the data you were given turns out to have been admissible. And that's our basic uniqueness result. If you have an admissible pair with the smoothness assumptions, then there's a unique minimizer. So this is what we were hoping for. We look at the variational problem. With that interior data, there is a unique minimizer. And for fans of stability results, Alex Tamasan proved one with Nashed about this very problem. 5 more minutes? Okay, so I will skip. This was our first sort of try and some weak convergence results at an algorithm. Which worked fairly well. So on this picture, I can just show you we start with an initial approximation, which is the curve with the pluses. After 5 iterations, you have the curve with, so this is a slice through a 2D picture to see things quantitatively. After 5 iterations, we are at the squares, and after 100 iterations, you have the exact, pretty much the exact reconstruction when there's no noise. And when there is some noise, I will show you in a moment, it's not super bad. Okay, so now a partial data result. The partial data result started from the observation that this is not really an elliptic problem. So basically, this tells you that if U is a solution, its level sets have to be minimal surfaces. So in 2D, this would be a geodesic. It tells you nothing about the behavior of U in the perpendicular direction. So why, if it's not an elliptic problem, why study the Dirichlet problem, even though others have done it? So what we said was the following. So, now, there's a basic restriction which I should mention, which is that we want the gradient of U to be non-zero inside. And that restricts us to dimensions 2, where there's a nice result by Giovanni Alessandrini, which tells you that if the boundary function, so if you have a sigma harmonic function, and you know that the boundary value function takes every value exactly twice, except possibly its minimum and its maximum. So think of it as going from -1 and then increases to +1. And same on the other side. Then guaranteed grad U is different from 0 inside the region. I believe it's an open problem in higher dimensions, right? Give me a condition on F to guarantee that in 3D. All right, so here's what we have. Suppose I can set up, I somehow know a priori that my potential is 2 to 1, but I only know it on this arc from A to B. So it's very simple. Take any value here and the corresponding value there. And you have magnitude J, so you have the metric. Find the geodesic that joins them. Now, how do we know there's a unique such geodesic? Right? For general metrics, there could be lots of them. But this is part of what we show. Suppose there is another one. These are equipotential lines for a solution of this elliptic PDE. And so by the maximum principle, if they're equal to this constant here and the same constant there, the solution is constant. If the solution is constant, its gradient is 0, contradicting that result. And so we know that for any two values on the boundary, there's in fact a unique geodesic joining them. And so here's our partial data result. We can now calculate U on that band and correspondingly the conductivity in that band. And then we noticed that to do so, you don't really need to know the metric here and here. But the statement is a little bit awkward. Let me give you the statement first, and then I'll tell you in practice what we do. Suppose you have two situations where the two magnitudes are the same in this band. In this band, so the band is for U1, and you assume magnitude of J2 matches magnitude of J1 in the set omega AB. Then the corresponding set for U2 is exactly the same. The two functions are the same, and so are the conductivities in that band. Well, nonetheless, in practice, if you tell me you can measure the magnitude of J in a band, how do I know if it satisfies this? To know that it's of this form, I basically need to know U, which is what I'm after. So what we do is the following. Suppose you give me U in a band. Magnitude J in here. I don't know it here, I don't know it there. So I extend it by continuity. I just make up an artificial one, and now I have a magnitude, I have a metric everywhere. And I take a value here between A and B. And I have a metric, and so I can calculate the geodesic joining these 2 points. And now 2 things happen. Either the geodesic stays inside the band you gave me, then I'm happy. Or, following this metric, or depending on how you extended this metric, the geodesic decides to leave the band. Or even, it's bad enough if it just wants to touch out there. If that's what it wants to do, we throw it out. And so we only keep the geodesics that stay inside here, which means we know they do not depend on how we extend it out there. And so on the region spanned by those geodesics, we can do what I just said, and we recover the conductivity. If no geodesic stays inside here, if they all somehow want to leave in the band that you gave me, then I declare defeat. I can't recover anything. That's our partial data. So there's 2 partial data results. One is when you know magnitude J everywhere, but U only on the boundary, then that's completely fine. And the other, which is stronger, okay, that's how we compute geodesics. Stronger, but as you saw, the region where you do it is a little bit awkward. Okay, so I have to stress this is simulated data. What we did is we just took a CT picture and we assigned conductivity values to the grayscale, somehow consistent with what's known about tissue. And then we computed the forward problem to obtain magnitude J. By we, I mean Alex Timonov, to calculate. So with the forward problem, we calculated the current, and that's our data. And with that data, we now compute the geodesics. So here you see the computed geodesics for the current corresponding to the conductivity you saw. Then there's an additional step which I haven't mentioned. When you do the discrete problem, you can't just compute sigma equals, even once you know U, you only know U at a discrete set of points, and so you need to do some sort of an extrapolation before you can compute the conductivity. So here's our partial data where we gave ourselves the magnitude of J only in this region. So it looks too good. You almost think that we took a perfectly nice picture and cut it with scissors. We did not. And in fact, if you look carefully here, there's some of the issues that I talked about where depending on how we extended the J, these geodesics over here and up there are not so reliable. But otherwise, the partial result you see works fairly well. And here it is with 1% noise, 5% noise. Looks like I have to stop. So with apologies to Amir, I was going to talk about his result about inclusions which are perfectly conducting and perfectly insulating. I kind of advertised that in that context, and I'll be happy to show you the preprint. Thanks.
have a question.
Yes, sir.
So if you go to more dimensional case, say 3 dimensional, so
Right.
you have this equipotential
Surface.
Line.
Surface.
Well, first line on the boundary.
Okay, line.
And then you know that it is a resulting will be zero mean curvature.
Right.
So that becomes a reasonable question.
Right.
How many uniqueness of this problem?
Right.
So is it?
So we have some sufficient condition, but it's not nice. I mean, we assume cylindrical geometry.
Uh-huh.
We assume the length of this boundary curve is less than 2 pi, and then there's something where you can say there's unique. But in general, right, for minimal surfaces, if the boundary curve is long,
Yes.
you might have non-uniqueness
Not
for the
non-unique.
Dirichlet problem.
Okay.
So we don't have much to declare at that point. There was some.
Other questions? Then thank you very much. And